Welcome back. So this is a brief introduction to section 1C, which is about three things. So first it's about whether a subset U okay, so I'm starting with a vector space. And I want to know whether a subset of this vector space is a vector space under the same operations. Operations as V. And the same operations is the important part. It's not just another vector space that lives in V, but it's a vector space under the same operations as V. And so then it's called a subspace of V. Okay, so that's the first of these ideas. And so it turns out, and we'll show, so the theorem will be U contained in V is a subspace is equivalent to having the zero vector from V in U. Okay, so we know the zero vectors in V, but we want it in U, and then we want just closure. So if we have two vectors in U, so U1 and U2 are in U, we know their sum is in V because this is an addition on V, but I want the sum to be in U. So it's closed under addition of vectors. Okay, that's clearly necessary for it to be a vector space. And then it also has to be closed under multiplication by a scalar. So if I have U in U, and I have a scalar alpha, and remember our scalars, these are real numbers or complex numbers, then again, I know in V I can multiply it. That'll make sense in V, but I want that to be in U. Okay, so these are clearly necessary conditions. It turns out they're sufficient conditions, and we'll show that in the next class. So just to have an example, so let's suppose I'm looking at U, which is four tuples of the form x, x, y, y, where these are real numbers, and that's contained in R4, just four tuples. Okay, so that's a subset of R4, and you have this, you can add vectors in U just like you could in R4, but I want to make sure, first of all, the zero vector is in there, but the zero vector is all zeros, and that's of this form. This is saying that the first two coordinates are the same and the second two coordinates are the same. And in fact, it has that form, so this is in U because it's of the right form. And if I take two things of that form, like an A, B, 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 and I add it to a C, C, D, D, okay, so this is adding two vectors in U, I get A plus C, B plus D, B plus D. The point is, these two are the same, these two are the same, that's enough to make it in U. Okay, and then multiplying by a scalar, if I have some number, and I multiply it by an A, B, B, X, X, Y, Y, I can use any symbols I want. The point is, these two coordinates are the same, and these two coordinates are the same. I get alpha A, alpha A, alpha B, alpha B. And so again, these two are the same, these two are the same, that makes it in U. So that means that this set U, this smaller set, is actually a vector space in its own right, and that's a subspace. So that's one of the three ideas that's in this section. The second idea that's in this section is about sums of subspaces. And we'll talk about, in class, we'll talk about a sum of a bunch of them. In other words, if I've got a bunch of subspaces, I want to add them all together. I'm just going to look at, in this introduction to 2. And so the point is, so I've got within V, I've maybe got 2 different subspaces that are vector spaces in their own right. And, so I know like the 0 vector is in both of them because you need a 0 vector. So maybe one of them is maybe this one is U1 and this one is U2. And we'd like to put them together to get the smallest subspace that contains them both. So, and we'll prove this, the smallest subspace, oh, come on, baby. Of V. So it's got to be a subspace. It's got to be closed, containing, in general, all of these UN1 through UN. But let's just talk about 2. And let's say this one's U1, this one's U2. This is V. So is the sum, which you just write as a sum, and it's what you think it is. It's all the sums of things where you take something in U1 and add it to, it's anything of this form. U1 in U1, U2 in U2. And so you can show that's a subspace, that the set of things, where you're adding 2 things together is a subspace, and it's the smallest subspace that contains them both. So notice that the union is not a subspace in general. So this sum is like the analog of a union, but for vector spaces. The reason it's not a subspace in general is if I take something here and then I take something over here and add them, there's no reason that it has to be in either place. Okay, so that's why I have to look at the set of sums, because I won't have sums. If I just were to take the union, those are the things that are in one thing or the other. And if I add these 2 different things, the sum doesn't have to be either place. So that's the sum of subspaces. And so this example that's in the text is if we have our U1 like I had a minute ago, just the things X, X, Y, Y. And again, this is where my X and Y are, say, in the reals. It could be in any field. And U2 is X, 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 Y. Yep, that's what I want. Again, for X, Y in R. So you can show, I showed you U1 as a subspace. In a similar way, you can show that U2 is a subspace. So these are subspaces of R4. So you can show that when you add these vectors together, what you're going to get is it'll be the case that the first 2 coordinates are going to be the same. Because I'm adding things like this, they're both going to be the same. This might be an A, and a B, and when I add them, I'm going to get the same thing here. But these other things could be different. And so this is for X, X, Y. Well, I don't need to write X twice. X, Y, Z in R. Okay, so it's not just the union, or intersection or anything. It's what you get when you add them together. And we'll look at this example again more carefully in class. So it is the case. So notice that in this particular example that these intersect. So this example is like my picture. I have a U1, a U2. They have some overlap. And as we noted, always 0 is going to be in the overlap because a subspace has to have 0. But here, you can see that actually this overlap, it certainly includes all the things where these are all equal. Okay, so it's more than just the 0 vector. And so in particular, if I'm writing a sum, so when I have this vector x, 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 I could think of that as being something in U1 plus the 0 vector, which is in U2, or I could think of it as the 0 vector plus x, x, x. In other words, where this is coming from U1 and this is coming from U2. In other words, I'm looking at sums here, but I don't have a unique way of writing them. And that's what a direct sum is. So that's the third thing. Okay, so if, again, more, you can have more, but let's just look at 2. So it's written, okay, and that's called a direct sum. If every vector in this sum is expressible uniquely. Okay, and so the point here is this unique. This is the important part as a sum. Okay, and notice anytime this intersection is non-zero, the 0 vector, the sum is not direct. Okay, and we'll show for 2 things that's going to actually be, it's going to characterize it. But so an example that is direct, so I might have like this plane. That might be my U1. And then just this line. And so now this sum is direct. Okay, because the only thing that's in both of them is the 0 vector. And so I can express everything uniquely as something in U1 plus something in U2. Okay, so we'll extend this to more subspaces and prove some of these things I just stated.